So atomic number will be defined either by the number of protons or number of electrons, right? Number of electrons in a neutral atom, right? Neutral atom. If it is an ion, then we can't decide the number of electrons for the purpose of atomic number. Only for the neutral species, number of protons and number of electrons would be same, and for ions they would be different, right? And we have a capital A which will denote atomic mass unit. We call it simply as AMU, right? AMU. So that is 1/12 of mass of carbon 612 atom. So you might have studied these isomers, isotopes. So carbon has the isotopes of carbon 12, carbon 13, and carbon 14, right? But we will consider only carbon 12 for the purpose of atomic mass unit definition. 1/12 of the mass of carbon 612 atom, right? And atomic weight of 6.023 into 10 to the power 23 molecules or atoms, right? So this is what called as atomic weight. So carbon has an atomic weight of 12.011 and hydrogen has 1.008. So these all are atomic weights, right? So this is just a brief introduction. So why I am saying this is, so these atoms, the electrons, protons, neutrons, are the main reason to determine the property of each and every material, right? Right. So atomic structure. Valence electrons determine all the following properties: chemical property, electrical property, thermal property, optical property, magnetical property. So there are different properties. These all would be determined by the valence electrons. So what are these valence electrons? So valence electrons are the electrons which are in the last shell of an atom, right? Last shell of an atom. So if you just draw an atom, right, and if you see, there will be a last cell, right? So if you take an atom, so I will take some X, right? So this is not an actual atom. So this will have a first shell, right? This may have a second cell also. Maybe this will have a third shell also, right? So imagine this is full, right? So the first shell, you know, can have only 2 electrons, right? And imagine this is also full, right? So this can have maximum of 8 electrons, right? Second shell. And now this one we have as the last shell, and say this will have only 2 electrons in this, right? So in this case, these 2 electrons are the valence electrons, right? These 2 are called as valence electrons, right? Valence electrons. So these valence electrons are the main part to determine these properties, right? So these electrons, they will not play that important role, right? They will not play that important role because it is a filled orbit, right? It is full actually. But this orbit has only 2 electrons, right? So either this one can give the electron to some other atom, right? Or it can share with some other atom, right? It can share with some other atom. So this one can do different things as per the requirement. So only this valence electron can do that. The electrons which are inside, right? The electrons which are inside can't do such things, right? So these are the electrons which are inside, right? So these electrons, they can't share or they can't go beyond to another atom. They can't do anything. They just have to sit in the orbit, right, and rotate. That's all they can do. But these electrons which are on the valence shell, right, these are on the valence shell, they can either go, if they wish to join with another atom, or they can share with another atom, right? So this shell we call it as, in another way, valence shell, right? So chemical properties are the properties about the reaction, right? So if sodium is reacting with chlorine, right, that is a chemical property, right? That's a chemical property because sodium is reacting with the chlorine and form a new compound, right? So this kind of reaction we call it as chemical properties. So chemical properties. Electrical property is a property to conduct the electricity or not conducting the electricity. They all are electrical properties. And thermal property also, conducting heat or not conducting heat, or expansion on heat. So say for example you have a metal of this length, right, with heat that may extend up to this length, right? So these all are coming in the thermal property, right? These all are thermal property. And then we have the optical property, right? So optical property, whether it is transparent or we can see it will leave light through it, these all will come under optical property. So electronic structure, right? So electrons, they have wave-like and particulate-like properties, right? So electrons, we know they have two type of nature. We would say two type of nature. So at a time they will exhibit wave property as well as particle property, right? So particle property mean that can be identified as a particle, right? At the same time, if it is a wave property, then in a proportion, right, we can say this is in this cloud, but we can't say where is actually. So wave like mean, you know, a wave, right? That is a wave, something like this, right? So you might have seen the sea, right? So this is a wave. So in a cloud, right? So if you take this as a nucleus, right, the electrons would be rotating in this orbit, right? Only the proton and neutron in the nucleus, you know that, right? So nucleus consists of neutron plus proton. And electrons, what would they do? They will be keep on rotating on the orbit, right? So in this time, they will have wave nature, right? So since they are moving here and there, we just can't say, okay, the electron is somewhere here, right? We can't say, oh yeah, I found the electrons, it is here, right? You can't say, because it would be keep on moving at a very fast rate. So we can say the electron is in this orbit, right? It is in this orbit, but we can't say, okay, electron is here, right? We can't say that. Just for the purpose of drawing this sharing and releasing of electrons and bonds, we draw, okay, this is one electron, this is one electron, something like that. But this is only for the purpose of studies. Actually, electron will not stay like this, right? It will keep on rotating the nucleus, right? So that's what meant by the wave-like nature. And particular property. So particular property mean electron is a particle, right? So it does have a mass, right? It has, so it is a particle, right? So electron can exhibit both wave and particulate properties, right? So these are the two properties. This means that electrons are in orbitals defined by a probability, right? So this can be defined as the probability in orbit. So if you consider this as an orbit, right? So this is an orbit. We can say, okay, electron is in this orbit, right? So that's a probability. Either it can be here, or it can be here, or it can be here, or it can be here. We can't say where it is actually. It's an orbit. Each orbital at discrete energy level determined by quantum numbers. So this orbit, right, maybe next orbit, this each orbit has its own energy, right? So that energy will be determined by this quantum number, right? This energy would be determined by this quantum number. So these four numbers we will use for the quantum number. Small n is principal energy level. We will say principal energy level shell, right? So the designation KLMNO, right? So if you just imagine, okay, I'll take calcium. So calcium is 2882, right? Okay. So KLMNO, what this meant by is the first level is determined by the K, right? So this is denoted as K, right? Then the next energy level, we will write it as L, okay? Then the next one, we write it as M, and then N, right? And when it is going upper, then we go for O and all, right? So this is what meant by this KLMNO. So principal energy level, right? So principal energy level. So in the calcium means first energy level, we will have 2 electrons, right? Then we will have 8, right? Second energy level, we will have 8. We will have 8, right? But that is not true, right? And only for calcium, we may have in the next one 2, but for different atoms, we have much more than that, right? So we'll see. This n principal energy level is each orbital is the principal energy. So first orbital is denoted by K, second one denoted by L, third one denoted by M, and fourth one denoted by N, right? So this is our calcium, right? Okay, so this is our primary energy level, right? And then we have L subsidiary orbitals, SPDF, right? So these subsidiary orbitals are orbitals which are further classified into this orbit. So for example, if you take this orbital, right, I'm going to draw this orbital now. So this is primary, right? If I draw it in secondary, this one will have an S orbit and an P orbit, right? The subsidiary orbit, so we will call it a secondary orbit also. So they will be denoted by small s, p, d, and f, right? So only these four. For the principal orbit, we have k, l, m, n, o, p, and all. But for secondary orbit, we have only these four, right? So this s can have a maximum of 2 electrons, right? And this p, it can have maximum of 6 electrons, right? And then we have d, right? So d can have 10 electrons, and f, we can have 14 electrons, right? So this is the maximum. So each main orbit would be divided into subsidiary orbit, right? But in the first orbit, there will be only s, right? So first orbit, there will be only s. In the second orbit, right? So that is L orbit. So this is your K, right? This is your K orbit. In L orbit, that is your second orbit, we will have S and P, okay? In the third orbit, so third orbit is our M, right? So in the M, we will have S and P and D, okay? S, P, and D, right? And N orbit, we will have S, P, D, and F, okay? Right? So what I'm trying to say is, if you consider K orbit, right, the maximum is 2 electron. Why? We can have only S, right? So S mean 2 electrons, right? Totally 2 electrons. So if you see here, right? This is our first orbit. We will now have only 1 and 2 orbits, right? So this is why we write the atomic structure of calcium as, so you might have write this one, right? Calcium 2 8 8 and 2. So in this way you might have write, right, already. So you know this way, but now I am saying why are we writing it that way, right? Why are we writing it that way? So since the first orbit can have maximum of 2, right? So our calcium we write first as 2, right? Now we go for the next orbit, right? The second orbit. In this second orbit, I told you S and P can be there, right? So S mean 12, sorry, not 12, 2, and P mean 6, right? So here 2 and 6. So how much is 2 and 6? Totally 8, right? So that's why in this orbit we can have maximum of 8 atoms, right? Maximum of 8 atoms, right? So similarly, when we are going in the third orbit, we can have 2, 6, and D I told you 10. So altogether we will have 10 plus 6 plus 2, 18 electrons, right? So this is the way these atomic numbers are arranged, right? Usually this SPDF is the maximum amount of electrons which can be sit in that orbit. This is our calcium, right? This is our calcium. But after calcium, we have these many elements, right? So the maximum number of electrons which can be filled is the number of the last element in this row, right? So first row maximum is 2, which means this is that 2, right? S group 2. Then that is 8, right? So that is 1, 2, 3, 4, 5, 6, 7, 8, right? So this is that 8, right? So for calcium, we stopped with 2, but in calcium, that orbit, we can have maximum of these many electrons. So this maximum number of electrons which can be admitted will be determined by this SPDF and this main orbit, right? So here you see, so this is how we will write, right? So for hydrogen 1s1, right? So in hydrogen, if you take that orbit, right, so maximum is 2 because it is in the first orbit, right? So helium 2, 1s2, right? So with these two elements, the first orbit is over. Why? Because the first orbit we can have only s, right? And in s the maximum is 2, right? As I told you, the maximum is 2, right? So here in the first orbital we can have maximum of 2 electrons, right? Then we go to the next orbit, right? So that is, I told you, if it is second orbit, then that is S and P, right? S and P. So in S you know 2 electrons. In P I told you 6 electrons. So 6 plus 2 is 8, right? So maximum in the second orbit we can have 8 electrons. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? So these are the second orbital elements. So that is from 3 to 10. So that is 8 elements in between, right? So for these 8 elements, this 2s and 2p part is the different thing, right? Because this 1s2, it is already filled orbital, right? So this 1s2 is already filled. So that will now come to all the elements which are below this, right? All the elements which are below this 1s2 will come. So now we are talking about the second orbit, right? So these all are coming in the second orbit. So if you take the periodic table, that will be coming like this, right? So this is our first orbit, 2 maximum. Then comes to our second orbit. That is what we are now talking about. That is 8, right? 8 electrons or 8 elements we can have. So what we are doing, we bring this 1s2, that will go for all elements. Now we are concentrating on 2, right? So this 2, right, while writing this 2 is the main orbit 2, right? There is a main orbit 2. So that is main orbit K is 1, L is 2, right? So if you are writing this as 2s1, right, this 2 belongs to the main orbit, right? And this S1, S2, P1, these all are belong to the secondary orbit, right? So secondary orbit is the orbit we have this S and P and D and all, right? So if we finish with the deal with the lithium, then we will go for beryllium, right? So for beryllium, there are totally 4 elements because this is 1, 2, then we have beryllium, that is 4, right? Beryllium, that is 4. So while writing beryllium, we will have these 2 at the start, 1 is 2, that will automatically come. Then now this is the second orbit, right? So we will write that 2, right? So this 2 is to show that it is in the second orbit, right? Then S2, right? So I told you S, the maximum is 2. Then we will write this S2, right? So for beryllium, that is S2, right? So this is the beryllium 1s2 and 2s2. So now if we talk about boron, it has 5 electrons, right? 5 electrons. So this is our boron and it has 5 electrons. So it has 2 electrons. So that is the 1s2, right? Then we have 3, 4, 5, extra 3 electrons, right? So 1s2 is the first orbit. So maximum is 2, that is done. Second orbit, we can have the maximum 8, right? For until 8, we can go. So we can't write 2s3, right? Why? Because in s orbit, the maximum is 2, right? So we will write 2s2 and then we will write 2p1, right? So this 2 is to show that it is in the second orbit, and this s and p, this p is to show the secondary orbit, right? Secondary orbit. So how we will write the boron 1s2, 2s2 and 2p1, right? So in s orbit, the maximum is 2, right? So until the last element neon, we will have 2s2, but the p will be keep on increasing, right? So 2p1, 2p2, 2p3, like that, p will be keep on increasing. So in neon, if you see, this is 2s2 and 2p6, right? So here s orbit 2 electrons, p orbital 6 electrons, 6 plus 2 is 8, right? So here we have the maximum of 8 electrons, right? Wherever we are finding s, right, the maximum would be s, I mean 2. It can be 1s or 2s or 3s. The maximum would be only 2, right? So if I write in this format, right, this 1 and this 2, right, and this 3, they are denoting the main orbit, right? So this is the main orbit. And then this S2, P2, P6, D10, these all are showing the suborbital, right? Secondary orbital. Right? So here is our main orbital and here is our suborbital. If I am taking the example of carbon, right? Carbon. So in your O-level days, you have written it as carbon 6, 12, right? So this 6 is our atomic number and this 12 is our mass number. But now we are not going to deal anything with the mass number. We will be concentrating only on the atomic number now, for now, right? So how to write this one is, so if you see, that is totally 6. So now we know how to draw that one, right? So carbon, in the first orbit it has 2, right? This you have already studied. And in the next orbit it will have 4, right? So altogether 1, 2, 3, 4, 5, 6. 6 electrons we have, fine, right? So how to write this one in the elaborated format, right? So in the first orbital it has 2 electrons. So we write it as first orbital, it will have 2 electrons, right? First orbital, 2 electrons, right? I already told you S maximum 2, E maximum 6, D maximum 10, and F maximum 14, right? So this is actually the maximum, right? So maximum means in the d orbit it can have 5, 6, 7, 8, 9, 10 is the maximum. In d orbit it can't have 11, right? So D11, it is wrong, right? It can't have D11. In a similar way, S3OP8 is also wrong, right? S3OP8 is also wrong because maximum in S is 2, maximum in P is 6. So if we write like P4 OS1 OD8, this is correct, right? Why correct? D8 is correct, P4 is correct, and this one is also correct because maximum it can have is S means 2, P means 6, and D means 10. So below this, any number is fine. But if it is D11, that is wrong. Then it must be D10 and F1. So it will be going in this order, right? If S is finished, then we will go for P. If P is finished, then we will go for D. If D is finished, then we will go for F, right? So now we come back to the carbon, right? In the first orbit, it has 2 electrons. So 1 is 2, that is fine. Next orbit, right? Next main orbit, it has 4 electrons. So that is second orbit. So second orbit means we will write 2, right? Second orbit means 2. And first is S, right? So we will go start with the S. How much should I write here to the S? 2, okay. Okay, why is that? So maximum number S can have is 2. So I will write 2. So if I see now 2 plus 2, I have 4 electrons. But altogether carbon has 6 electrons. So now I should go for which number? Okay, P. Why is that? Okay, so in the second orbital we have only S and P. So I will write P. That's fine, correct. And now which number should I write? Here.
2, because already 4 electrons filled, then remaining is 2.
Okay, fine, correct. Because this is our first orbit, so this is 1s2. Why? Because only 2 electrons are there, that is this 2. First orbit, so that is this 1, and in the first orbit only S can be there, so that is this S, right? So in the second orbit, this is our 2, that is for second orbit, right? And this is S, and 2 why we are writing is maximum it can have is 2, right? So if 2 is finished, but we still have 2 electrons, so then we will go for P. Yes. In each orbit, we should start with S. Each new orbit, right? If it is first orbit, then we should start with 1s. If it is second orbit, then we should start with 2s. In the third orbit, then we should start with 3s. So once the S orbit finish only, we can go for. So when we are done with the 2s and still there are electrons, then we can go for 2p, right? So this 2 is for second orbit, and we still have 2 more electrons, right? So 2p, 2, right? So if you see totally now 2 plus 2 plus 2, that is 6, right? So carbon atomic number is 6, that we have 2 plus 2 plus 2, 6 electrons we have.
We can, why we are give the elements like this are 1s2 1 2s2 like that, we can directly give the numbers, no? Why we are given like this?
If you directly give the number, you can't find which is the valence electrons. So in the previous previous lecture, I told valence electrons the last orbital electrons now, which can move here and there. So those elements will determine the most of the properties, whether it's covalent bond or ionic bond, or it can give or it can gain. So those things will be determined by this. So if we write like this, we can find, okay, so s orbital is complete now, right? No need to deal with this. So now we have this p orbit half, which means second orbit is not filled yet, right? So in order to for these properties, we will write like this. So then we can directly see, okay, this orbital is not filled, right? So when we are talking about aluminium, if first orbital is finished, by just looking at this one, we can say, okay, first orbital part is done. So we don't have to deal anything with this first orbit. And when I see to the second orbit, 2s2, 2p6. So we know in the second orbit, only s and p should be there, and maximum should be 8. So 2 plus 6 is 8. So this is also fine. And then we move to the third orbit. There we will find, okay, only p1 and 3s2 is there. So only 3 electrons filled, and there are a lot of space for the electrons to fill. And in the third orbit only space left, right? So these minute data we can see only if we write in this format, right? So this is why we break it into this small format and write electron energy states, right? So this is the energy increasing order, right? Energy increasing order. So this is also a reason why we should write regularly to 1s2, then 2s2, then 2p6, then 3s2, 3p6, like this, right? So this is the state of energy, right? So if it is 1s2, it has certain energy, right? So that is some low level energy, right? So if you see, the energy is increasing in this way, right? So this is one orbit, and when it is go to the second orbit, energy is little bit high, right? Energy is little bit high. So actually S level energy is lower than the P level energy, right? So we will write S first and then we will go for the P, right? So this is your main shell K, right? K main shell, that is first orbit, right? K, that is first orbit. L main shell, second orbit, right? M main shell, third orbit, right? N main shell, fourth orbit. See, n is equal to 4, that is n, that is fourth orbit. N is equal to 3, that is m, that is third orbit, right? So this is the ascending order of the energy, right? Ascending order of the energy. So while filling, these electrons should be start from bottom and keep on going to the top of the energy level, right? So first we will finish with fix with 1s2, then 2s2, then 2p6, then 3s2, then 3p6. It would be going like this.
Sir, why sir 3S, 3P, 3D? Why sir 4S come like that?
Okay, this is the question I was expecting. Fine, right? So when we are filling in the table, right? Table in the sense the periodic table, right? When we are filling in the periodic table, these atoms will fall in the order of energy, right? So when we are talking about the energy, until this level, you all are fine, right? So according to what I taught so far, 1s, 2s, then 2p, 3s, 3p is there. But what you will expect is 3d should come here, right? Then only 4s should come. So the case is not like that. Really, the 4s have lesser energy than the 3d. Okay, 4s have lesser energy than 3d. So while filling, what will happen? We will fill 4s first, and then only we will go for 3d, right? So we will fix like 1s, 2s, 2p, 3s, 3p, then we will fix 4s, and then we will go for 3d. This is because the energy, right? So each energy level has its own energy, right? So in that sense, 4s energy is lesser than the 3d energy. So there are several factors for that. There are several effects like shielding effect, screening effect, and there are so many effects. So if I talk about that, then that will go deep into chemistry. So what I'm simply saying is energy level difference is the reason for this one. So this is the reason why we put this 4s ahead of this 3d, right? And next thing, why do we have these lines? So this line, in each line, there can be 2 electrons stay, right? So if you think about a bike, right? In bike, usually two people can sit, right? Usually in a bike, 2 people can sit. So like this, in these electrons also, in each this dash, only 2 electrons can stay, right? So that I have in the next cell, I think, right? So if one electron fill in this way, right, the other electrons we put it in the opposite way because we call it as spin, right? So electrons, I told you, they have the particle and wave nature. So wave nature, in the sense, they will be keep on rotating like this, right? So while rotating like this, they will automatically rotate them also. So like our Earth rotating itself and rounding the sun, right? So electrons also, they rotate themselves and rotate in the revolve in the orbit, right? So this is what the magnetic property coming from. If one electron rotate in the clockwise direction, the other electron in the same orbit will rotate in the anti-clockwise direction, right? So they are a pair, right? Pair. If it is s electrons, then we will have 2, right? Maximum 2. If it is p, then we have 1, 2, 3, 4, 5, 6, right? So p orbit we have 6. I will take the periodic table, right? So you see this one, right? You see this one just, so there is a 3p and then there's a 4s, then 3d, right? You have this one in mind. We'll see here. So here we have 1s. So this is first orbital, right? So I have 1s, right? Then I have the next orbital. So this is 1 and only s is there. Here I have the second orbit, right? There I have 2s and p, right? Then I have the third orbit, right? So this is our third orbit. So according to what I say, third orbit must have s and p and d, right? I told you now, first orbit is s maximum 2, second orbit s and p maximum 8, that is 2 and 6. So first orbit 2, second orbit 2 and 6, third orbit 2 and 6, and there is a d, that is 10. So that is totally 18. 10 plus 6 is 16 plus 2, 18, right? But if you see in this periodic table, right, in this periodic table, so first orbit 2, right, 1, 2 elements are there, that is fine. Second orbit, there must be 2 plus 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. That is also fine. I have 8. In the third orbit, I must have 2 plus 6 is 8 plus 10. How much? 18. If I see here, I have 1, 2, 3, 4, 5, 6, 7, 8. I have only 8. So I have only this 8 is there. So now my question is, what happened to that this 10? So there must be 18 according to our formula. but in the periodic table only 8 is there. So what happened to this 10? Right, so what actually happened is this 10 which are supposed to be here in this region, right, they are here, right? So these are these 10 elements, they are supposed to be in this region, right, but they are here. Why? Because is, if you see, that's what I was talking about, the energy diagram, right? So if you see, so you see this one, right? So these elements are those 10 elements which are to be here, right? So if you now remember about this energy diagram, right? So there must be 1s2, right? I'm talking about the ascending order, right? 1s2, then 2s2, right? Then 2p6, then 3s2, then 3p6. Then what was there in the energy diagram?
4s.
4s, right? 4s2. Then after this 3d10. Okay, right? So now we will see. So 1s2, 1s2, right? This is fine. Then I have 2s2. So 2s2 is second orbit, 2 electrons. That is also fine. Then I have 2p6. So 1s2, 2s2 is over. 2p1, 2, 3, 4, 5, 6. This 2p6 is also fine. I have. Then I must have 3s2, right? So 3s2 is here. That is also fine. Then I must have 3p6. 1, 2, 3, 4, 5, 6. Right? 3p6 also I have. Fine. Then I have 4s2. Right? I have 4s2. 1, 2, 3, 4. So this is fourth orbit. I have 2 electrons. Then 4s2 part is fine. After that, it is coming to 3d10, right? So that is this 3d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is how this periodic table is actually written, right? Periodic table is written based on the energy of the elements, right? So if you see, this is the ascending order of the energy. So as I told you, I was coming across one by one. So after 3p6, then we have 4s2, then it is coming to 3d10, right? So this is the reason why we don't have these 10 elements here. If we have it here, then this should come after 3s2, we must have 3d10, then we should have 3p6, isn't it? So this is your third orbit. So for these two elements, we will write 3s2, right? And if I put this, if they are here in this region, then that is 3d10. Then for these things, I will write 3p6, right? 3p6. But according to our energy level, it should come like this, right? S, P, D, and F. So if I write this like this, then S is there, then D is coming, then P is coming. So S, D, P. So this basic formula is being violated, right? So this is the reason why we don't have these 3D elements here, but we have these elements here, right? So this is the reason why this 4s is coming ahead of 3d. Due to the energy arrangement, we arrange this periodic table, and due to this arrangement only, these elements are coming ahead. So this is how these electrons will be filled, right? So one arrow we will put one side and the other arrow we will put the opposite side, because to denote the opposite spin of the electrons, right? Opposite spin in the sense I already told. So if one electron is rotating in the clockwise direction, the other electron would be rotating in the anti-clockwise, right? So these two will fix in this particular line, right? So this is common for all, right? So in each and every line there can be maximum of 2 electrons, right? Maximum of 2 electrons. So if one orbit is filled, then you have to go for the next orbital. So if one is you fill with 2 electrons, then you may have to go to the next level, 2s 1 electron, 2s another electron. And also while filling, right, if you see this d, right, if you see this d orbital, only one is there in the opposite direction, but all these 4 are in the same direction. Why can't we denote like this? One this way, one this way, one this way, one this way, like this. So rotate 2, 3, 4, 5, 6. So maybe in like 3 lines, we can denote this like 6. 1, 2, 3, 4, 5, 6. So why don't we denote like this, but why should we denote like this? What's the reason? Right. So this is the nature of the electrons, right? So when they fill in an orbit, right, usually they take less often. So you see, so if you are going to somewhere, right, a new place, you will be happy if there is no opponent, right? If there is what would you like if you in a tournament, whether going in a bye or to fight with another team and go? Which one do you prefer? If it's a knockout tournament, right, getting a bye and going is one way. Fight in the first round and going to the second round is another way. Which way you prefer?
By
Bye, right?
directly.
Yeah, directly going is the preference way. So that's a nature. So electrons is also going according to that nature. So if they are coming to a this single line and staying, they are more than happy because there are no opposite spin, right? So at the start, what would they do? They will come and fill directly the empty these suborbitals, right? So if all 5 are filled, then the 6th electron which is coming from somewhere does not have any place to stay. So it has to adjust with the already available electron, right? So then that would be the less preferred path, right? So this is the reason why it is filled in this way and not in this way, right? If it is in this way, there's an electron, then another electron is coming and it need to fill like this. If there is a vacant orbitals, then why is it going to the share with this electron? It will not go, right? So that will go to the empty orbitals. Once the empty orbitals are finished, then after that the coming electrons, they do not have a place to stay. Then anyhow they need to stay with the other electrons, right? So this is why the empty shells are get filled first, and then there would be next electron would be come and sharing, right? So this is a reason why we don't have in such a way, but why we have in this way, right? And here, right? So Fe, that is iron. So we are talking about the atomic number, right? Electronic configuration. 1s2, that is here, right? Then 2s2, 2p6, 2s2, 2p6, that is also fine, right? Then I have 3s2, 3p6, right? 3s2, 3p6, that is also fine. That is 8, right? Here also 8. Here we have 2, right? And then it has 4s2 and 3d10, right? So 4s2 and 3d10, they are in the next available orbit. So that is why they are valence electrons. So these electrons are going to design about the properties of this Fe, right? So these electrons, they will not have any impact on that about the deciding the properties. But these two valence electron cells, they will determine the properties, right? So this is why we need to see the number of and where are they staying, the valence electrons, right? So they are the reason for most of the properties, right? So this is simple example for Fe, right? So what I am saying now is very important. There are two special cases, right? Two special cases. Atomic number 24, probably it must be chromium, and atomic number 29, I hope that one would be copper, right? So if it is 24, right, 2 plus 2 plus 6 is 10, 2 plus 6 is 18, right? This 2, so up to this region it is okay. So problem is coming after this. So they are using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Up to this 18, it is okay, right? So there are how many electrons? Totally 6 electrons are there. So according to what we should write, we will write. So 6 electrons we need to write off because already 18 is done, right? So up to this one, it is written. I'm talking about 24 now. I'm talking about 24. So now I have to write what? 4s2. That is our usual practice, right? So that is 18 plus 2, 20. Then 3d4, right? So 18 plus 2, 20, 20 plus 4, 24. Okay, right? But, right, this 24 and this 29 are very special cases while writing this configuration. What they would do is, so 3d4 means we have this electron, this electron, this one, and this one, right? 4 electrons we have. But here we have 2 electrons. So what this electron will do is, it will jump to this empty space, right? Due to the energy, it will jump to this space. So the 24, we will not write it as 4s2 3d4, but we will write 4s1 3d5, right? So if this electron jump here, we will not have one electron here. So that is 4s1. And if it is jumping here, then we have already 4. This one is 5, right? So this stage we will say as semi-filled stage, right? So this is a special case, right? So there's an empty space, right? This electron would not like to be stayed here. So what will it do? It will jump to that empty space. So in writing, we will not write it as 4s2 3d4, but we will write it as 4s1 3d5, right? So this 24 is a special case. Similarly, the 29, right? 29 also there's a special case. So in 29, after this 18, we will fill this 2 and that is 20. Then here we will have 9, right? 18 plus 2, 20. We have excess of 9. So we will write it as, so I have like 5 shells. So I will fill like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this 3d orbit should be appearing like this, but the 4s orbit should be appearing like this, right? 4s. So similar thing in the case of Cu also. this empty electron, right, this will not stay in this location. What it will do is it will jump to this position, right, and it will become like this, right? So this electron will be jumping here and will be coming like this. So there won't be any electron here, right? So there also we will not write it as 4s2 3d9. We will not write like this, but we will write like 4s1 3d10, right? So this way we will write. So this is fully filled state. So why is that is these electrons, due to the stage of full, right, fill stage, or if it is like completely filled, then we don't have to talk anything about valency, right? So if it is completely filled, then we don't have to talk about valency, which means there is no energy discussion here, right? There is energy, but we are not going to discuss about it because it is not going to share, or it is not going to go away with and couple with another electron. That's nothing is going to happen. So for that reason only, this electron will jump up here, which means this is completely filled, right? So we are not going to discuss anything about this valence shell now, right? So only this would be now in discussion. Why? Because 3D is now 10, right? So 3D is filled, 3s is filled, 3p is filled, 3d is filled. So there is no discussion about 3D now. Only 4s would be the deciding factor of the valence, right? So this is the reason why this 29 and 24 are special cases, right? So 25, it will, I mean, in the sense that will expect to achieve the half filled 3D5 stage, and this will expect to achieve the full filled 3D10 stage, right? So this is the speciality with the 24th atomic number and 29th. So that must be chromium and copper, right? So only these two are the special cases while writing this electronic configuration.
Sir,
Oh yeah.
first we want to fill the third 3D, sir.
No, because according to energy, it will be keep on fixing, right? So in energy, 4s is ahead of 3d. So once you fill with 4s only, it will go to the 3d. Because that's how our periodic table is also designed, right? So if you see, after K, potassium and calcium, right? K is 19, calcium is 20, right? Then only we will go for the D block elements, right? D block elements. We call that as D block elements. There are 3 rows, each consists of 10 elements, right? So there are totally 30. So we call them as 3 D block elements or transition elements. So after calcium only they will come. So once you fill with 4s2 only, we will be talking anything about D. So valence electrons, those in unfilled shells, right? So they are in the last shell or unfilled shells. Filled shells are more stable, right? So that's why I told in this case, right? It will try to 24 and 29. It will try to achieve either half filled or full filled state, so that it would be stable, right? So that is why the case of 24 and 29, they would try to be stable. Valence electrons are most available for bonding and tend to control the chemical properties, right? So I told about the chemical properties, right? So these are responsible for the chemical properties, because whether the bond is ionic bond or covalent bond or hydrogen bond, stronger or not stronger, these all would be determined by the number of valence electrons, right? Not number of valence electrons, actually number of valence electrons, as well as where are they existing, right? So this is the reason why we are paying much attention on the valence electrons, right? So in carbon, valence electrons are these last 4, right? So 1s2 shell is complete. So now we don't have anything to do with that. Second shell, right? We have 2 plus 2, 4 valence electrons. If it is coming 2p6, then that is complete, right? So if I have the electron configuration 2s2 and 2p6, then which is complete, right? So 1s2 already complete. So 2s2 and 2p6 if I get, then that is complete. Until it is achieved in 2p6, all those in the last shell are valence electrons. So until 2s2 and 2p5, right? These are valence electrons. These all are valence electron. If it achieves 1s2 and 2p6, then there is no valence electron. So that is more stable. So this is our last 8 column elements. They are inert gases, right? So we have helium, then neon, argon, krypton, xenon, right? So these all are stable, more stable because they have last orbit filled, right? I mean last orbit filled. So there are no more valence electrons, right? So this is the reason why we pay much attention on valence number, right? There's a formula to, you don't need to memorize, okay, S have 2, P have 6, something like that. Based on this number, right? Based on this number, you can determine how many maximum electrons can be there. So the formula is 2n square, right? So if you substitute 1 here, you will have 2 into 1 square, that is 1, that is 2. So we can have maximum of 2 electrons in the first shell. Second shell, 2 into 2 squared. So 2 squared is 4, 4 into 2, 8. So in the second shell, we can have total 8. You see, 2 plus 2 plus 2 plus 2, that is 8, right? In the third shell, that is 2 into 3 squared. So 3 squared is 9, 9 into 2 is 18, right? So 3s2, 3p6, and 3d10. So if you add together 10 plus 6 plus 2, that is 18, right? So this is a formula we use to find number of electrons. You don't need to memorize.